Okay, this video we're going to look at fundamentals of probability, which is basically just an introduction to probability. And unfortunately, I'm back to the laptop because I want to be able to flip back and forth between the whiteboard and a couple of tables and charts. Okay, so let's go to the whiteboard. And remember, when I'm on the laptop with my very limited technology, it's a little messy. Okay, all right, so fundamentals of probability. There are a couple of definitions that you need to know. First is an experiment, okay? An experiment is any occurrence where the outcome is uncertain. Okay, and in this class, we're going to do a lot with flipping coins and decks of cards. I promise I'm not going to make you, I'm not going to turn you into a gambler by any stretch of the imagination, but you do need to be familiar with a deck of cards because we're going to be using a deck of cards for a lot of these questions and pretty much every section that's going to come up after this. Okay, so understand rolling a die, flipping a coin, rolling a die is another one. So rolling a die, flipping a coin, and decks of cards, those are the three big ones for us, okay? Especially rolling a die and decks of cards. We'll also look at like little spinners. You know how some games have the little spinners where you've got like a circle that's broken into equal pieces and you got the spinner and you flick the spinner and it's got an equal chance of landing on any of these pieces. So those types of things are going to come up quite a bit. And the biggest one for students is understanding a deck of cards. Again, you just got to understand it because it's kind of part of this section. So it is part of what we're testing you on, okay? Now, an experiment, again, it's any occurrence in which the outcome is uncertain. So you draw a card from a deck, you don't know what that card's going to be. You flip a coin, you don't know if it's going to land heads up or tails up. And then rolling a die, you have no idea what side the die is going to land on. Okay, so the outcome is uncertain. We then have a sample space, and the sample space is really big. That's going to be something that comes up throughout this section, really throughout this chapter, but a sample space is the set of all possible outcomes of an experiment. Okay, so it is the set of all possible outcomes for an experiment. Okay, so if you're dealing with flipping a coin, the possible outcomes are heads or tails. If you're rolling a fair six-sided die, the possibilities are the numbers 1 through 6. If you're dealing with a deck of cards, you've got a ton of different possibilities, 52 in fact, okay? And we'll dive into the deck of cards in just a bit, okay? So when we're talking about computing probability, we have basically two types of probability. We have theoretical versus empirical. And a lot of what we're going to do is theoretical, but we will look at the empirical too. Theoretical is kind of like what could happen. Empirical is what we observe. So with empirical probability, it's what we actually see happen. So you'll have a lot of times with empirical probability, you'll have like these data sets. So you'll have these tables with lots of information that was actually observed versus theoretical. It's like what could happen. So like if I roll a die, what is the probability that it lands on a 7? Well, 0, that can't happen. What is the probability that it lands on a number less than 7? Well, that's 100% because that's every option. And then you could do something like, what is the probability that I land on a 5? Well, that could happen, and it's 1 out of 6 possibilities, okay? So when we're dealing with probabilities, we're looking at probabilities anywhere from 0 to 100, or for us, because we don't really do percents, we do more like the decimal side of things, we're going to be dealing with fractions and decimals a lot in this chapter, okay? So when we're talking probabilities, it's going to be some number from 0 to 1, okay? So let's go and look at theoretical probability first. Again, this is what could happen. So in theory, if I roll a die, what is the probability this could happen? So for theoretical probability, we always write it the probability of whatever. So capital P, and then in parentheses, you put the probability of what you're looking for. So we're just going to use E, the probability of this particular experiment, all right, or this event. So it's the number of outcomes for whatever E is divided by the total possible outcomes. All right. So basically, we're going to say that we're going to do that whole rolling a die thing. So let's say, what is the probability of rolling an even number? Well, the event that we're looking at is an even number. So if you're talking about a fair six-sided die, how many ways could you roll an even number? Well, you could roll a 2, you could roll a 4, or you could roll a 6. So there would be 3 possibilities for that particular event, E. Now, for the whole experiment, rolling a die, what are all of the possible outcomes? Well, there are 6 possible outcomes. So the probability of rolling an even number, we would take the number of outcomes for the specific thing we're looking for. So rolling an even number, that was 3. And then you divide it by all possible outcomes, which in this case would have been 6. Okay, so let's look at some examples. So we are going to be rolling a 6-sided die. So just in case you didn't know, dice, that's the plural. The singular is die, which sounds a little morbid, but that's what it is. So we're going to be rolling a fair 6-sided die. Find the following probabilities. So for the first one, let's look at the probability of rolling a 3. Okay. The way we would write this is we would write it as P with a 3 on the inside. That 3 tells us that the event we're looking for. What is the chance that we would roll a 3? Well, on a fair 6-sided die, there is 1, 3, and there are 6 possible outcomes. So the probability of rolling a 3 would be 1/6. Okay. Next up, we want to know the probability of rolling a 2. So the probability and then the event we would be looking at would be a 2. Okay. On a fair 6-sided die, how many 2s are there? There would just be the 1. And then there are 6 possible outcomes. So again, the probability would be 1/6. So the chances of rolling a die and landing on a 2, 1 out of 6. And then 3, we have exactly what I laid out for you before, an even number. So we could write that as the probability, and then inside we could just put even. Well, there are 3 even numbers, 1 through 6. So it would be 2, 4, or 6. So that's 3 different options for this event. And then there are 6 outcomes total. So the probability would be 3 out of 6. But when we're dealing with probabilities written in fraction form, we always want to reduce. So the probability is actually 1/2. So half of the options on a fair 6-sided die are even. All right, next we want to look at a number less than 4. So I would write that as the probability, and then inside parentheses, I'd find some way to denote less than 4. Well, if you're dealing with a fair 6-sided die, numbers that are less than 4 would be 1, 2, and 3. So there are 3 different ways that you could roll a number less than 4. So we get 3/6. But just like in the previous example, we would want to reduce. So this reduces to 1/2. All right. Next up, we have a number less than 5. So again, we would find some way to write that in parentheses, so just less than 5. So if you think of the numbers 1 through 6 that are less than 5, you have 1, 2, 3, and 4. So there are 4 possibilities for this event, and there are 6 possibilities total. Okay, so it's going to be 4 over, in this case, the sample space is the total possible outcomes. And then you want to reduce this. 4 and 6 are both divisible by 2. So 4 divided by 2 is 2. 6 divided by 2 is 3. And then finally, we want a number less than 7. Well, if you're dealing with a fair 6-sided die, all possibilities are less than 7. So you could have 1, 2, 3, 4, 5, or 6. So you get 6 possibilities for that event out of 6 possible outcomes. So the probability here is 1. It's a sure thing. It's absolutely happening. Okay. Now, what if I did one more example? This is not on the worksheet, but let's just pretend. What if I did a number greater than 6? Well, that would be P of greater than 6. Well, how many numbers on a fair six-sided die are greater than 6? Well, none of them, because the options are 1, 2, 3, 4, 5, and 6. So we would get 0 out of 6, or a probability of 0. So you can have anything between 0 and 1. 1 is a sure thing, it's happening. 0 means it's never, ever, ever going to happen. And then everything in between is somewhere between 1 and 0. So something that's really low, close to 0, it's not very likely to happen. Something that's much higher, closer to 1, it's much more likely to have happened. Okay. Or to happen, rather. All right, next up, we want to talk about a deck of cards, okay? And this is super important. I hate to do this to you, but you have to learn a deck of cards. So part of what you're going to be graded on in this class is understanding a deck of cards, okay? It's not impossible. There's a pattern to it, but you got to understand it, okay? So let's take a quick peek at the worksheet. Hopefully it is in color on my screen. Indeed it is. So it's a little bit hard to see because it is blown up, but basically there are what we call suits. There are 4 suits in a deck of cards. You've got hearts, clubs, diamonds, and spades, okay? Each suit contains 13 cards. So if we annotate this, there are 4 suits, 13 cards each. So that's a grand total of 52 cards. You're dealing with a 52 card deck, okay? That means there are 13 hearts, 13 spades, 13 diamonds, and 13 clubs, 13 diamonds, 13 spades, okay? So hearts and diamonds, notice they're red. So that means we have 26 red cards. And then clubs and spades are black. So that means we have 26 black cards. Okay. And then you've got what we call face cards. These are your face cards right here. There are 3 face cards per suit. So 3 faces per suit. So that's 12 face cards total. Okay. All of these things that I'm listing out are really important. Okay. All of these numbers are going to be used repeatedly, okay? So you have to understand a deck of cards, period, no questions, okay? So you've got hearts and diamonds, those are red. There are 26 red cards, 13 diamonds, 13 hearts. There are clubs and spades, those are black cards. There are 26 black cards, 13 spades, 13 clubs. That gives you 52 cards total. And of those 52 cards, 12 of them have faces on them, either jacks, queens, or kings, okay? So you have this in your worksheet, make note of it. Now, the only problem is when I printed your worksheet, I did not print it in color. So you need to make note that spades and clubs are black, hearts and diamonds are red. Again, I'm never going to make you into a gambler, so there's going to be no moral dilemma here, but you do need to be familiar with a deck of cards, okay? So let's go. I need to scoot this over just a smidge. Let's go back to the whiteboard. Okay. So now we're going to be dealing with decks of cards. So the next example is you are dealt one card from a standard 52 card deck. Find the probability of. I really do wish that I had better technology because I swear my penmanship is much better than this. But anyway, so the first thing we're going to look for is an ace. So we want the probability of an ace. So we would write it like this. Now each suit has 1 ace. So there are 4 aces in a deck. There's the ace of hearts, the ace of clubs, the ace of diamonds, and the ace of spades. Okay, so there are 4 possible aces in a deck that is made out of 52 cards. You do want to reduce this. So for every 13 cards, there's 1 ace. Okay. Next, we want a red king. So I want the probability of a red king. You got to find some way to denote this. I'm going to do RK for red king. Now there are 4 kings in a deck. There's a king of hearts, a king of clubs, a king of diamonds, and a king of spades. Only 2 of those are red. So 2 out of 52 cards would be a red king. So that's going to be 1 out of 26 cards is a red king. Okay. Let's see what's next. We want just a red card next. So we want the probability of drawing a red card. Now, out of the 52 cards, you've got 13 hearts that are red, and then you've got 13 diamonds that are also red. That's a total of 26 cards that are red. So 26 out of 52, or 1/2 of your deck of cards would be red. Okay. D, we want the probability of a spade. So those are the black cards that look kind of like a little shovel. Okay, so we want the probability of a spade. Well, that's one entire suit. So remember, there's 13 diamonds, 13 clubs, 13 hearts, and then there are 13 spades. So that's going to be 13 out of 52, or one whole suit. So 1/4 of your deck of cards. Okay. Next, we want to know the probability of a face card. So the probability of a face. Now remember, there's jack, kings, and queens. Okay. There's a jack, a king, and a queen for hearts, a jack, a king, and a queen for clubs, a jack, a king, and a queen for diamonds, and then a jack, a king, and a queen for spades. So that's 3 face cards for each of the 4 suits. So that tells me there are 12 face cards out of 52. And you do want to reduce this, okay? So we would get 3/13. So for every 13 cards, 3 of them would be faces, okay? And remember, that kind of makes sense because for each suit, 3 of those 13 cards would be faces. Finally, we want to know the probability of getting the 3 of spades. Forgot my A. So we want the probability for the 3 of spades. Well, within the spades, you have an ace, a 2, a 3, a 4, a 5, a 6, a 7, an 8, a 9, a 10, a jack, a queen, and a king. Only one of those spades that I just listed was a 3. So that's going to be 1 out of 52. Okay, so out of all 52 cards, only one of them is exactly the 3 of spades. Okay, now what if I did one more? What if I did the probability of getting a green card? Well, in a standard 52 card deck, the cards are either black or they are red. There are no cards that are green. So this would be 0. Okay. So remember, 0 means it's never going to happen. A probability of 1 means it's always going to happen. And then the other probabilities are somewhere in between. Okay. So that's that for a deck of cards. Make sure you're able to recognize a deck of cards. Make sure you understand the 4 suits, the different colors, the face cards, the whole kit and caboodle. Okay. And again, it is part of what I'm grading you on. So you are required to learn this. All right. Now let's talk empirical probability. So empirical probability is what we actually observe. So data that is observed. I really wish I had better technology. And one day I'm going to spend a ton of money and I'm going to make my setup better. So this is data that is observed or observed data. Okay. So contrast to equally likely outcomes with theoretical probability, this is what we actually see. Okay. So with theoretical probability, the examples we did before with rolling a die and pulling a deck of cards or pulling a card out of the deck, we're like, hey, if we have a deck of cards, what is the probability that we would get this? Okay. In empirical probability, you're looking at data that was actually observed. Okay. So it's a little different than theoretical probability. All right. So if we want to write this out, the probability of some event occurring, we want the observed number of times whatever the event is, however many times that occurs that we witness. And I swear that says occurs. It looks like a, but it's occurs, okay? And then we want the total number of observed occurrences. So we're going to look at two different examples. We're going to look at one example that talks about the marital status of Americans in a certain age group, and then we're going to talk about educational attainment of Americans in a certain age group, okay? This is observed data at some point, okay? And I mean, the data is going to be a little old at this point, but it's actual observed data. So when you're talking marital status, we might be looking at the number of people that are married out of all people in this particular age group. So the numerator, the event would be the number of people that are married, and then the total observed occurrences would be all of the people that fit the bill. So all of the people in America in that particular age group. Okay. And that is what we're going to look at in the first example. So it says in 2015, there were approximately 254 million Americans ages 15 or older. The distribution by marital status and gender in this population is displayed in the following table. Numbers are expressed in millions. Okay. So then we are asked, if one person is randomly selected from the population, find the probability to the nearest hundredth. So that means we're no longer doing reduced fractions. We're going to be writing our answers as decimals. And that's a big thing. Default with probability, always write your answer as a fraction unless otherwise stated. And here it's stated that we do want to write our answers as decimals. Okay. So the first thing I want to do is go and look at this particular table. Okay. So here we are. So it says again, in 2015, there were approximately 254 adults. I want to make note of that. This is the big total. Okay, that's everything. That's the 250 million Americans ages 15 or older. Okay, the distribution by marital status and gender of this population is displayed in this table. So you've got it broken down male, female. So let's do some new colors. So we're going to say male is red. The total males would be 123 million. Okay, let's do green for female. So female is green. There are 131 million females. If you add up 123 million and 131 million, what do you get? You get the blue total, 254. Now, let's say that we did, I don't know, I'm kind of out of colors, but let's say yellow is married. There are 133 million people in this table that are married. Let's do pink. Never married. There are 81 million Americans in this age group that were never married at that point. We could do dark green, divorced. There were 26 million that were divorced. And then let's do purple. That would be widowed. You had 14 million. If I add 133, the yellow number, 81, the pink number, 26, the dark green number, and 14, the purple number, that's going to add up to 254 million. Okay. So the last column and the last row, they have to add up to be 254 million. That's how you read this table. Okay. So if we're looking at the probability that somebody is divorced, so let's go to just black ink here. We want to look at the total number of people divorced out of the total number of people in this table. So the denominator is going to be 254. But what do you think the numerator would be? It would be the total number of divorced people. So it would be 26. Okay. Now, if you take that and put it into a calculator and you round it to the nearest hundredth, you get 0.0. No, you get 0.10. Hold tight. I wrote that wrong. You get 0.10. Okay. That's it. Okay. The difference here is we're not writing it as a fraction. The directions told us to write it as a decimal, but you're just pulling information from a table. This is actual information from back in 2015. Now, next up, let's say we wanted to find the probability that somebody was female. Well, if you look at the total in the table, everybody considered in this table was 254 million people. But of the 254 million, we want to look at the females, which are the light green color. That was 131 million of the people in the table. So you would take 131 million, divide it by 254, and that's going to give you the probability that somebody from the table was a woman, which is 0.52. Okay. Now, next up, we have the probability that somebody was never married. So I'm going to do NM, never married. Again, the denominator, we're looking at the whole table here, is 254. But of the 254 million people represented in this table, how many at that point in time could currently say they were never married? Well, that's the pink number. That would be 81. And if we took 81 and divided it by 254, we would get 0.32. So basically 32% of this table had never married from ages 15 up back in 2015. Now, if we wanted to do the probability that somebody was male, all right, again, the total in this table is 254. That's not changing. But of those, how many are males? So we want to look at male, which I circled in red. Well, 123 million people in this table were male. And if we take 123 divided by the total people considered in this table, we would get 0.48. So approximately 48% of this table was male. Okay, so this is empirical probability. We're looking at actual data. The total number of occurrences would be the total in that bottom right-hand corner. Okay, sometimes you will be given tables that have not been filled out. So they'll give you all of the male, female, married, never married, divorced, and widowed, but they don't give you the totals. So in some cases, you have to do a little work to get the totals. But this is how you'd read one of these tables. The bottom right-hand corner, that's the total for everything. And then you look for specific values in the table and put them over that number. Okay. Later in this chapter, we'll look at different types of probabilities and you approach a table like this very differently. But for this one, we're just looking at the occurrences of a particular event over the total number of occurrences observed. Okay, so let's go back to the whiteboard. All right, so we talked about that. We already did the never married. We have another one. Well, I guess I could have stayed on that sheet because we're not really looking at any other definitions. But we do have another table now. We're looking at the educational attainment in millions of US population ages 25 and older. So we have it broken down male, female, less than 4 years of high school, 4 years of high school only. So like the highest education attainment was 4 years of high school. We then have some college, but less than 4 years. And then we have 4 years or more. So we're looking at kind of like the highest attainment at that point when these people were 25, okay, or older. Hold tight, I need some water. So just remember, when we do empirical probability, we're looking at actual observed data, and we're looking at the observed numbers of times a particular event occurred over all observances. So for this table with educational attainment, we're looking at 174 million Americans. That's going to be the denominator. And then the specific groups we look at. So if we look at somebody with exactly 4 years of high school only, that will go in the numerator. Okay, so let's go back to the worksheet. And we're going to scroll down a smidge. That'll work. There we go. Okay, so we're going to kind of break this down in colors again, just like we did before. So let's say that we have the light blue color. That is our total. This is everybody in the table. So there are 174 million Americans that we're looking at in this table. So we're looking at Americans that were 25 years or older, and we're looking at their educational attainment. Okay. So if we did male and female, there are 82 million males in this table. And then there were 92 million females. If I take 82 and I add it to 92, I get 174. So that totals column works. All right. We then have less than 4 years of high school. There were 29 million people. We could look at 4 years of high school only, 56 million people. We could look at some college, but not 4 years. That was 44 million people. And then finally, we could look at 4 years of college or more. That was 45 million people. So if I add up those colored numbers on the bottom, 29 plus 56 plus 44 plus 45, that's going to give me a total of 174 million. Okay. So the problem says find the probability expressed as a simplified fraction. Okay. Make note of how they want the answer. In this case, they want simplified fractions. Okay, that a randomly selected American ages 25 or older is going to fit one of these categories. So we want the probability that this person had less than 4 years of high school. So I'm just going to do less than 4 and then HS for high school. Okay. Well, the total in this table is 174 million, no matter what. Of the 174 million people in this table, how many had an educational attainment of less than 4 years of high school? Well, 29 million. And then you can put this in your calculator and simplify it. So if you've got a graphing calculator, I don't actually have the graphing calculator up, but if you have a graphing calculator, you can literally do 29 divided by 174, hit enter, it's going to give you a decimal. And then there's a math button, which is directly below alpha. Hit the math button. The first option is to turn your answer into a fraction, so hit enter. And then it's going to pop up on the screen and it's going to kind of ask you to verify, do you want your answer as a fraction? Hit enter again, and it'll reduce your fraction and you should get 1/6. So 1/6 of this table, 1/6 of Americans 25 years or older at whatever time period this was taken, they had the highest educational attainment of less than 4 years of high school. Now, we want the probability for the next one of 4 years of high school. So they went ahead and they finished up high school. They just did the 4 years. So again, the total in this table is 174. But of this 174 million people in the table, how many finished high school and then didn't do any more education? Well, that would be the pink number, 56. So again, in your calculator, you would type in 56 divided by 174, hit enter, hit the math button, which is directly below alpha, and then hit enter twice. And you should get 28/87. So 28/87 of this table finished high school. Okay. So next up, we have, in this case, it's a little bit more specific. So we have very specifically women with 4 years of college or more. So I'm not sure how to write that. So I'm going to do probability of women 4 years of college or more. So that's a little wordy there, and pretend you can read it. I know you can't because it's messy as all get out, but just pretend, okay? I get my feelings hurt with how bad my penmanship looks when I use my laptop. Now, looking at this particular table, we want to look very specifically at women and women that finished more than 4 years of college, or they finished 4 years of college or more. So if I look at the female column, I get all the way down to the purple stuff, and I have 22. So 22 million women finished college or did more than that. So they did 4 years of college or more. And again, that's out of the total 174 million. And if you do the whole numerator divided by denominator and then turn it into a fraction, you get 11 out of 87. So 11/87 of this table were or consisted of women that finished 4 years of college or more. Okay. And then finally, we want men with 4 years of college or more. So we want the probability of men with 4 years of college or more. That one you can read a little better. All right. So again, we're going to go to the men, the row for males, and then we're going to go to the column that was purple, and we have 23 million men finished 4 years of college or more. So we do 23 over 174. And again, you could do the same thing, 23 divided by 174. See if your calculator will turn it into a fraction. In this case, this is as reduced as it's going to get. So this would be your final answer. So 23 out of 174 million people consisted of men with 4 years of college or more. Okay, so that's it for our introduction to probability. Okay, there we are. So we've already talked about the fundamental counting principles. So if you're dealing with choosing items from groups, how many ways could you get a certain combination of things or a certain setup? And then we did the fundamentals of probability here. So if you have any questions, let me know. Always read your book. There's more information. There's more examples. There's all sorts of stuff in your book. But otherwise, that's it for this worksheet. If you have any questions, let me know.